which is on spectroscopy 1. The science of spectroscopy is frankly the science of rainbows. And if we look at the sun, if we spread the light out into all of its constituent colors, what you'll see is a rainbow of colors and some missing lines. And we discussed the Kirchhoff's laws, where all stars produce something called an absorption spectrum, where all colors are present except for some missing lines. But if we look over here, we see the spectra of just very hot gases, and rather than having dark missing colors, we see mainly hardly any colors except specific ones for each element, and each element has its own unique number of colored lines called emission spectral lines. And so the idea here is we're going to look at two gases. We're going to spread the light out coming from each gas into its emission spectra, those bright, very colorful lines. What we do know, like I say, is that those spectral lines that we find in these hot gases are really like fingerprints that we find at a crime scene. What we know is that at a crime scene, if you find a fingerprint and you can identify who has that, is a unique fingerprint for one individual in this world. No fingerprint duplicates a second fingerprint from another person. And that's true about the patterns of colors in the spectra of stars. Now, what we have here is the setup. And what we have is this black fixture that provides high voltage that passes through a gas tube. And in that gas tube is a low pressure gas, in this case, hydrogen. Now, hydrogen produces its own particular pattern of colors, but when they mingle together so that we see the resultant color is this beautiful purple. And so what we're going to do is we're going to utilize a little device. It's this guy right here is in a little slide. And it's hard to see this, but optically, or really mechanically, they scribed lines, very fine lines, packed together very tightly in a little small distance called a millimeter. There's over 700 lines scribed in there. And this is called a diffraction grating. And what a diffraction grating does, behaves like that crystal hanging from your mirror from your car, you know, the one that's hanging right by your big dice in your car. And that crystal, what does it do? Well, when sunlight passes through it, what you'll see, silhouetted on the seat covers, you know, those nice high, cattle seat covers you have, the black and white ones. You'll see a rainbow of colors. That separates the mingled colors from the sun into its rainbow of colors. We're going to use this to take the light out of this gas, hydrogen, and spread it out. And then we're going to make a couple of measurements. And from that, and using the theory of the laboratory, which we'll tell you in videos provided for you, we will be able to find the wavelengths of each particular spectral line for this particular gas. And then we'll repeat that same process by removing this tube and placing a second tube in there holding helium gas. So this is very low pressure, but with the very high voltage, this is very hot gas. And that's why it glows in that beautiful color that we see. Now, if you remember from your lecture class, if you look at the type of nebula, large clouds of gas and dust found in space called nebulae, the emission nebulae glow with that same color right there. Because just like this gas, the atoms are excited, the electrons are basically transitioned to higher orbits. Remember, that means the atom has more energy than what it likes to have. So nature doesn't want that to be the case. So what happens is the electrons have to travel back down to their original orbits. But to do so, they have to release that energy that they gained to allow them to go to higher orbits. And the way it releases that energy is by emitting light, photons, of each particular color we see in the spectrum of this gas. And again, it's an emission spectrum. So this is the setup. We have one large ruler right here. Why don't you come over here? One ruler right here is it's what will give us what we call basically the measurement for Y. And then there's a smaller crossed ruler that will give us the measurement of X. And it turns out that in this little ruler is a small window right here that we want to line this tube up. Now, probably need to make that a little higher, excuse me. So I'm going to go ahead and get some lab jacks. Lab jacks are just used to raise experimental apparatus higher. To get close to the diffraction grating, to see if you can see the color spectral lines. In hydrogen, you'll see a beautiful red, a very beautiful aquamarine, like a green, and then a wonderful violet. The whole setup is cheap. And because of that, we have to take into account errors. And so what we do is we actually measure two distances for X for each spectral line. And then we find the average of those to separate out some error that we might have because these are cheap. I mean, these diffraction gratings might be $1 or at the most. Whereas the diffraction gratings used at the observatories can be tens of thousands of dollars. And the reason why they're so expensive is that they're so carefully made. So, what are we going to measure? We measure the distance from the window over to the diffraction grating. That's Y. Then we're going to measure along this. It starts at 0 in the middle, goes out to 15 centimeters to the right, looking through the diffraction grating, and 15 centimeters from 0 in the middle again out to the left. And what we're going to do is find those distances, Y, only one of those for each gas, and then two measurements of X for each particular color. So there'll be a total of 6 measurements of X for hydrogen, and it turns out that there'll be 8 measurements of X and a different value of Y for helium. And the reason why there's 8 measurements of X is that unlike hydrogen, which is red, aquamarine, and violet, helium has spectral lines of a different shade, meaning a different wavelength of red, a beautiful orange, and another shade of green, and a different shade of violet, where the shades mean that they vary slightly in wavelength from these here. So what we're going to do, we're going to go ahead and make the measurements for you for Y and for X for hydrogen. Then we'll repeat this with helium. And we'll probably go ahead and quickly film what helium looks like so you get a sense of how those mingled colors produces a different total color than hydrogen does. Experiment from those measurements of X and Y, and from the calculations that will provide you from the experiment, you will be able to calculate the wavelengths of each spectral line for hydrogen and for helium. Then when you've got those experimental measured values of the wavelengths of spectral lines for hydrogen and helium, you will compare them to the true and actual wavelengths of those spectral lines that we know are true, measured with a much nicer setup than we have. And what you'll do is you'll compare that with something called the percent error. Remember what we said about percent error? Percent error is where you find how much difference a measured value or an experimental value is from the true value. And the equation for that calculation is in your lab textbook. Now we differentiate that from percent difference, and you've used that in the class. Percent difference is where we have two measured or experimental values for a particular property that we're measuring. And we don't compare it to an actual value, but you're comparing those two experimental values. Percent difference, we're not using that now. Percent error, because we do know what the wavelengths are. Okay guys, so we'll take these measurements, we'll provide those values, and then we'll teach you how to use this to determine the wavelengths of the spectral lines. Okay, so we've removed the tube with hydrogen in it, and now we'll take out the gas discharge tube, that's what these are called, filled with helium gas. Place it in the fixture with it turned off, because you know there's nothing like being totally caffeinated by touching 5,000 volts, and that's not what we want to do. Turn this on. Now notice that the mixture of colors is completely different from what we had for hydrogen. I would say that this is more like a ultra attractive salmon color. And so now what we do is we place it up against the large ruler for measurement of Y. And now what we do is we don't assume that the Y position, which is the distance from the cross ruler to the diffraction gradient, is the same amount. So what I do is I look in here and I reposition this so that all the spectral lines are basically, oh, I've lost my little balance. There we go. Okay. Okay. So now what I have this, I move this back and forth, so I place the spectral lines, which are red, orange, green, and violet, are within the ruler, but as far out and spread out as much as possible, but still on the ruler. And by the way, for hydrogen, it was also the same arrangement of colors. There's red farthest away from the center on the cross hatch ruler, then the aquamarine closer in, and then the violet closest in. And that arrangement is the same. So what we'll do now is we'll provide the measurements for the Y position, and then the X values for the 4 spectral lines of red, orange, green, and violet for helium. And eventually we'll give all this data to you. Okay guys, we'll take these measurements, and we'll stop this video right now.